Can you hear me? Hello?
Yes, sir.
Can you hear me?
Yes, sir.
Hello? Just count that. Hello? Can you hear
Yes,
me?
sir. Yes, sir.
Hello?
Yes, sir.
Hello? Hello? Well, I'm starting cluster points. Okay. Hello? You can hear me? Hello? Can you hear me?
Yes, sir.
It's very strange. Can you hear me?
Sir, yes, we can.
Hello?
Yes, sir.
Can you hear me?
Yes,
Hello?
sir. Hello, sir.
I'm starting cluster points. Hello? Okay.
Yes, sir.
Now I can hear. Note that cluster points and subsequential limits. Said given a sequence xn, if it converges, it's fine. If it is converges, then it's fine. Nothing to do worry about, because you get a point around which the members gather. But if the question is if xn doesn't converge, then how it behaves? How it behaves? That is the question. That means still whether its behavior is fine or not, how much the behavior is bad and how much is the behavior is good. In order to measure this, in order to measure its behavior, actually we need to look at the cluster points. Look, cluster points, that from the terms suggest that basically now it doesn't converge, so whether you will have more than one point around which members of the sequence, infinitely many members, of course not all, infinitely many members are gathering. Okay, so still that means still it's good that if I know the cluster points, I know only around these points many members of the sequence gather. Still through cluster points I will be able to know how is the sequence, like this sequence. This, though it is not convergent, it is still behavior, it's fine because its member is -1, 1, -1 like this. That means basically you can say half the members gather around other there -1 and other half gather around 1. Still it's good actually. Okay, so it is not convergent, but among non-convergent sequences probably it is one of the best sequences. So that in general looking for the cluster points. Now look what cluster points will do, how to define the definition 1. I want basically, suppose this X, now I will call it a cluster point. I basically want that whatever neighborhood of X you choose, X minus epsilon, X plus epsilon, could have deltas. That infinitely many members, not eventually, infinitely. Look, those members may not be distinct, but many members, here the members are not distinct. Many members of Xn are here, are in this neighborhood. That means infinitely many members, though not eventually, they are gathering around X. So how do you ensure? Through a precise definition. That means whatever, look, I am infinitely many. First of all, epsilon is given, but epsilon is arbitrarily chosen. But once you have chosen, it's fixed. Then I am saying infinitely many. That means you give me any natural number n naught, x n naught, even if it is itself, it may be there. If it is not there, I will get another n1 greater than n naught, such that xn1 is here. That means whatever, now you say, I give you another natural number. Not another n naught. That was bigger. Suppose I choose, now look, if I give you n1 now, okay, right? Or n1 plus 1 you take. Then this says I will get another n2 such that bigger than this, such that xn2 belongs there. That means this way I ensure that subsequence basically you're picking up. Look, I am picking up subsequence. N1 greater than n0, n2 greater than n1 plus n1 I have taken. That means n2 greater than n1. So that means I can pick up a sequence which will be in this neighborhood. So that will guarantee in particular that infinitely many members of the sequence are here. That exactly the definition I am writing. Let xn be a real sequence. Here everything real sequence. Okay. Then x is called a cluster point in given n naught and epsilon. Now, look, xn is a sequence. I'm talking about definition 1, page 36. Page 36. Xn is a sequence, okay, and x is called a cluster point. You should understand, should spend some time to understand this definition. Called a cluster point. If given, that if given means for any. That means given n naught belongs to n and epsilon greater than 0. Look, epsilon greater than 0 means you are taking any neighborhood of, this means any neighborhood of x basically. At any n, you get an integer n that I wrote. There exists n belongs to n such that n bigger than n naught. Now look, I said n depends on this n. Of course, depends on both n naught and this epsilon. That means neighborhood, such that I have this. But this precisely what I was explaining, that xn belongs to x minus epsilon to x plus epsilon, this neighborhood. This is again I am telling any neighborhood, that means you see. That means xn belongs to this. This is called the cluster points. The definition, we are to find only one n. Okay, but if you keep changing, basically you will get infinitely many. But to check if the cluster point, it is enough to find one. Now look, some authors call cluster points by limit points. That I told you, I do not prefer to use the term limit point, because in the sequence we can limit, if it converges we call it limit. So many students then confuse between limit points and limit. Even if you use this limit point for cluster points, make sure in the sequence when you say we just, if it converges we just use the word limit, whereas here limit point, that this is extra. But this is same as cluster. So altogether, to avoid confusion, you should better use this term cluster point. Okay. Now in order to see that, given epsilon, keep it fixed, but then I explained that actually already I explained that theorem, but now I'm going to share how to have a nice characterization of cluster point. This is subsequence. First of all, then means subsequential limit. What does it mean? That word, the term I'm explaining, subsequential limit of a sequence. You can write x is called a subsequential limit of subsequential limit, not sequential limit, of xn if there exists a subsequence. There exists a subsequence xnk of xn such that xnk converges to x. Look, if a sequence converges and if to a point x, then every subsequence also will converge to x. So there will be, we have only one subsequential limit, that is same as the limit of the sequence. But the if sequence does not converge, then maybe there will be more than one subsequential limit. So this is subsequential limit. Now we are giving a characterization of cluster points, okay, through subsequence. That is theorem 4.4, page 23 of the. So let me explain that in the proof. Okay. So proof actually, if you understand the idea already of the subsequence, it is not difficult to understand. So that here I am saying this theorem, page 36. Okay. This theorem is saying you are having a real sequence. Let xn be a real sequence. And x is a real number. Then x is a cluster point. This is the result. X is a cluster point of the sequence xn if and only if and only there exists a subsequence xkn of xn such that That means the definition of subsequential limit I have given you. Every cluster point is a subsequential limit and vice versa. Okay. So every cluster point means actually a subsequential limit. Now look, first suppose I have given X cluster point. First suppose X is a cluster point. Look, already I told you that how to pick up a subsequence. Okay, but I need to ensure that it converges to that cluster point. Now look, that's the trick. Each time, look what I am doing. First I am choosing epsilon equal to 1. Then you are getting a point xk1. Okay. Then you are choosing epsilon equal to half. I am changing the neighborhoods of x. Then you are getting a point k2. Look, here when you are choosing epsilon, there are two things you have to choose. Epsilon. Here you could actually you are choosing epsilon equal to 1 and the integer you are choosing 1. So k1 equal to greater than 1. Here you are choosing epsilon equal to half in the definition of cluster point. And the integer you are choosing k1, which you have already chosen. That means you will get k2 greater than k1 and you will get epsilon equal to half. That means x k2 minus x is half. Okay. In YAL, if you choose epsilon equal to 1 by n and then you are choosing the 2, this is 1. Then previously you have got it kn minus 1. Then you are getting x kn such that kn greater than kn minus 1 and x kn minus x less than 1 by n. Try to understand the trick. First of all, look, here when you are going to subsequential limit, you need to ensure two things, that you are picking up a subsequence. That means you are strictly following the definition of the subsequence. And also it converges to x. Two things you need to pick up a subsequence. And it converges to x, that cluster point converges. Two things you need to ensure. Now look how I am doing it. This is a standard trick. Okay, in analysis. Later on in metric space you will be doing the same thing. So look what I have done. Look, each time by definition of cluster point I am picking up the next kn which is bigger than kn minus 1. That means I'll have to keep kn minus 1 so that I choose this. So this ensures that I am picking up a subsequence. And look here 1 by n. This ensures that xkn goes to x because 1 by n converges to 0. 1 by n converges to 0. So this ensures that this. So this is the trick. 1 by n. Okay, you could take 1 by 2 to the power n also. But this, whatever you do, you need to ensure. That's the way you are picking up. That ensure this goes to x. So that you are doing. But another thing, it is not written here. You say, actually, it is written here. Actually, then in YAL we can. I have written. We need to continue this process in YAL for epsilon equal to 1 by n. So we need an induction process. Look, I have done, but this is not the entire proof because this is the process. If I do it, I'll have to continue indefinitely. That means you need to have the induction process. That look, that I explained in the next paragraph. Suppose K1, K2, Kn have been selected such that K1 less than K2 less than Kn and xki minus x distance between them is less than 1 by n. 1 less than equal to I less than equal to n. Look, this is only finitely many points, so I can do this process. Then for the pair, look here, epsilon equal to 1 by n plus 1 and kn. Okay, I have taken this n minus 1. I have chosen up to kn. So that's why it has been, next stage it will be 1 by n plus 1 and this will be kn. Such that by the definition of cluster point you choose this. Now note that I am getting exactly this. So this way induction process is over. Induction process says what? If we can choose up to n elements, I can choose n plus 1 cell. That's it. Okay. So that exactly do. So that induction process in the proof you need. You just say just continue this process, that is a wrong proof, wrong statement. You'll have to say that by induction process. Okay, so induction process, that is very important. That is why I have underlined induction. Okay, so this is the way you get subsequential limit. Look, I have written, if you want to write it more rigorously, then do it as follows. Given epsilon greater than 0, choose n not belongs to n. Now you want to show the convergence. That one not less than epsilon. Okay. Look, after I have chosen, then you want to prove that x kn goes to x. Okay. Now say if you want to do it rigorously, now choose any epsilon. You'll have to show that any epsilon neighborhood of x contains infinitely many members of the eventually the members of the substitute. That I have showed. That I think you understand. You should read it. Basically, trick is you choose any epsilon, then you choose n naught such that you have this. Then for all n greater than equal to n naught, this will be 1 by n. But this thing, that's the way I have chosen. The way I have chosen. Look, xkn minus x mod less than 1 by n. That is this because of this 1 by n naught. So this is less than epsilon. So this. Now the thing is that, so this is fine. And conversely, I think that's much easier that since you are having a subsequence converging to x, that means infinitely many members of the sequence, a sequence gathering around x, clustering around x, then you can see that. Okay, so I'm not repeating in this. So you should read that, the converse part. That is easier to say that. Subsequential limit is a subsequential limit implies cluster point. This is easy. On the other part, that cluster point, look, here you have subsequence. Just use the definition, you'll get to the cluster point. But cluster point, when you come this direction, then the thing is that you'll have to manufacture a subsequence that is which will converge to x. Understand? So that's the thing. You'll have to construct. It's not like differential equation, some problem you are doing this equal to this equal to this. It is not that. You'll have to construct. Okay, that you should keep in that mind. Okay, so now you have got it. So that I have written. So cluster point is nothing but a subsequential limit. That is the limit of a subsequence. I have written, note that for a convergent sequence xn, it has only one cluster point, which is the limit of xn. Look, if you have a convergent sequence, every subsequence also converges to that point. That means the convergent sequence has only one cluster point. In fact, sometimes you check that way, whether sequence converges. If we can show that a sequence has only one cluster point, then it must converge to that point. Like as a unique cluster point. Look here, that I mentioned, the top of the page 38, that more precisely, if a bounded sequence has a unique cluster point, does it converge? In fact, okay, that exactly the question, that if a bounded sequence has a unique cluster point, does it converge? Okay, well, it has to be converged, because if it doesn't converge, then hello, say again.
All subsequence converges to the cluster point, then we can say the sequence also converges.
Now look, page 38, look at my statement. Before that, just see that. What is my question then? Okay. If you have a convergent sequence, of course, suppose you have a convergent sequence. Xn. Xn is a convergent sequence, implies Xn has a unique cluster point. This you can just prove by using the previous result, which just now I proved. Okay, because xn, if is a convergent sequence, then by definition of convergence of sequence, every subsequence will converge to, suppose xn goes to x, then every subsequence will also converge to x. But any cluster point will give you a subsequence converged to x. Okay, so that x, any subsequence, suppose you take a cluster point y, that means you will get a subsequence converging to y. But since xn converges to x, so any subsequence x can also converge to x, but you are getting another thing. If you think, just choose any cluster point, whatever, xn goes to y, but then I have already shown that every convergent sequence has a unique limit. So x has to be equal to y. Got it? X has to be equal to y. Actually, xn convergent sequence, if you want to prove, now look, let me tell you. You can write as a small problem or result. Let xn be a sequence converging to x. Then x is the only cluster point. Only cluster point of x. Look, how will you prove? You will prove just as let y be a cluster point of xn. Then by result, what I proved, that just theorem. Then by that theorem, then there exists a subsequence xkn of xn such that xkn converges to
y.
But now, since xn converges to x, any subsequence will also converge to x, implies xkn converges to x also. Okay, since any subsequence of a convergent sequence also will converge to x. But now look this. Here, every convergent sequence has a unique limit. Here, the convergent sequence concerned is xkn. Okay, implies y equal to
X.
X.
That's the proof. X is the only cluster point. समझ गया? Since x is a limit of the sequence, obviously it is a cluster point. Okay, by definition. Okay, and I am saying that any other cluster point has to be equal to x. Okay, so there is only one. Geometrically, it is very immediate. Only around x they are gathering. Around no other point it is gathering. So x has to be the unique cluster point. Now the question is that other direction I am asking. Suppose I have a sequence such that this is the only cluster point. Then will it be this? So question I can ask you this thing. Let xn be a real sequence. Look, I have actually assumed when I defined for this, okay, cluster point, okay, so that, well, let xn be a real sequence, and suppose that x is the only cluster point x. Now the question is, xn converges to x. Okay.
No, sir.
No. No, sir.
No,
No,
sir.
sir.
X is the
can
only
have to bound
cluster
it.
point. Why no?
Yes, sir. Yes, sir.
No, sir.
X have to be bounded.
No, sir.
We can create a sequence.
Sir, we can define
Okay,
sequence.
fine. Okay, that one person I think what student was saying, every convergent sequence will have to be a bounded sequence first of all, right? So let me write xn be a bounded real sequence. ठीक है? उसके बाद बताओ.
Yes, sir. Now.
Yes.
But actually,
sir.
I didn't need this thing also because when I say x is the only cluster point, I think can you prove from here that xn has to be bounded? Forget about convergence. That suppose x is the only cluster point. X is a real number. I am working everything on the inside the real. I am not working on the extended real line. So you can have this question. If x is the only cluster point, of a sequence xn, is then if x is xn the sequence bounded then? Okay.
Sir,
Yes,
not
I
necessarily.
bounded.
Why it will be
No, sir.
bounded or
No.
not?
No,
No,
sir.
sir.
Yeah?
No, sir, not bonded.
I think bounded.
So we can define a sequence like
बताओ.
for even it is 1 by n, and for odd it is n. So 0 is the only cluster point, but it is not bounded.
Yes, you are right. Because they look at the trick. One part you are keeping it a convergent part, other one you are having your choice. You are making unbounded. That means you can take x1 equal to 1, x2 equal to 2 plus 1, something you can write, or 2 plus 2, x3 equal to 1 by half. समझ गया? x4 3 plus 3. Understand? That what even he was doing in that. That means if he is even, I can take 2n, or I can take simply n also. I don't need 2 plus 2. Take xn equal to n if n is even. And you take xn equal to 1 by n if n is odd. Okay? Then look, this is not a bounded sequence, but it has got only one cluster point in the real line. That is 0. Okay? So that, no. Fine? So that this also answers your question. Don't direction. If I don't give you this, then it's not true. It may not be true. Understand? Because this example, next example, question 2. Did you get the point? So that if this has to be true, then you need bounded. Then you should again check that. That means let x1 be a bounded real sequence, and suppose that x is the only cluster point of it. Does this converge? Okay. Actually, to answer this question, you can try, but you can read that in page 38. I have asked several questions related to that. All these questions I have answered. Okay, after getting all these questions answered, then you will realize that it has to be. Now look, what has to? First of all, I asked, does every bounded sequence have a cluster point? That's the first thing you need. Okay. Second, if a bounded sequence has more than one cluster point, will it have a minimum cluster point and a maximum cluster point? Understand? First of all, every question I have simple question. If it is a bounded sequence, well, will it have a cluster point or not? Okay. Secondly, if you have, so that means already in the example you have given that if you have a cluster point, it may not be bounded. But my question is different. I am saying if you have a bounded sequence, will it have a count? That means I am working with the bounded sequence now. Okay. I am working with bounded sequence now. I'm not going for unbounded sequence. That already you have given me an example. That if it is
Yes, sir.
unbounded,
It will have a cluster point.
Question is that you are saying it will have a cluster point. So that's the first question. Will it have a cluster point or not? And next thing that if you have a cluster, more than one cluster points, you can have infinitely many cluster points. But whether the set of cluster points will be bounded or not, in particular, whether you have a minimum cluster point or maximum cluster point. That's a question 2. And question 3, suppose that Xn is a
Sir,
bounded
if the sequence is itself bounded,
then
Set of
sir, if the
cluster
sequence
points
is
also
itself
bounded.
points
bounded,
also
then
bounded.
but
set of
cluster
cluster
point will
point will
move.
also
Some
bound.
members may be outside the neighborhood. Okay, right? So you'll have to prove it. Anyway, I'm coming to that. Okay, and then if you have a bounded sequence, that I'm saying. So suppose it is bounded by this. Basically, precise question is this: whether cluster points of the sequence, cluster points. If we answered question 1 and 2, then whether cluster points will be a subset of this interval. Okay, will be contained in this interval or not, if you have this. Okay, now look.
Yes, sir.
Yes. Yes, fine. So how to answer that? Before making further on this sequence, okay, working further on this sequence, we would like to note the following things. Okay, now look. First of all, first question is tricky. That how would I know a bounded sequence will have a cluster point? Okay, because if a bounded sequence doesn't have cluster point, my other questions do not make sense. Basically, they are not required. They become backward. Okay, if it happens, it doesn't have any cluster point, then question 2 and 3 they are backwards. They do not make sense. So that how to get that bounded sequence will have a cluster point? Will have. This I need to prove. Understood that? Okay. Now look, in order to prove this, actually we'll define two subsequences, and we do it indirectly. In the sense, we find two subsequences of this. They may not be distinct, there are two subsequences. And those subsequences converge. But already I have shown that any cluster point is same as a subsequential limit. So that means it will show that it will have a cluster point. In order to show that, I will show that Xn has a bounded sequence, has a subsequential limit. That means the bounded sequence has a subsequence which converges to a point. So that it will have a cluster point. In order to do it, okay, first just note the simple thing. Okay, wait a minute. That suppose you have two sets, A, B, non-empty sets, of course. Okay, and of course you can assume that here I have taken the other way. So let me finish it. Otherwise, you'll be confused with what is in the node. Suppose you have it, and of course, suppose this assume it is bounded. Any subset of a bounded set is bounded. So this is bounded. So that bounded means it is bounded above and bounded below, both. That means infimum, supremum exists. That means you have in fe, sup A here. Similarly, you have in B, sub B. Then what will be the relation? Okay. Now look here, you can easily check that in fe will be less than equal to in B.
P.
Okay, the reason is very simple. Look, in fe means what? It implies, suppose in fe you call M. M less than equal to A for all A belongs to A. Okay, but B is a subset of A, so that it implies M less than equal to B for all B belongs to B. But look, these have proved only that M is a lower bound for B. M is a lower bound for B, but inf B by definition means the greatest lower bound of B. So that M has to be less than equal to inf B. Got it? Okay, just
Yes,
use the
sir.
definition. Here
Yes,
I'm
sir.
using definition of lower bound and definition of greatest lower bound. But when you go for soup, it will reverse. That means soup of A will be the same way arguments will be greater than equal to soup B. Okay, that exactly I have proved. Okay, that's look here. I have proved. If A is a non-empty bounded subset of R, then every non-empty bounded sub is also bounded. Moreover, soup B is less than equal to soup A. Inf A less than equal to inf V. Now, okay, wait a minute. Now, how I'll use this thing? Okay, to create a subsequence of xn such that xn converges some subsequence, not all subsequence. Okay. Okay, convergent subsequences. Now look here, I've given definition. Look, yn we're defining. So xk k greater than equal to n. For each n in this, that is for each natural number we are defining. Look, it makes sense because you are taking xn is a bounded sequence. So if you have all these members, bounded sequence means what? This is bounded, this set is bounded. And this here, if you take this, look, xk k greater than equal to n. Don't confuse with this n. This n is a variable n. It can have anything. This n is you have been given here. So this is a subset of this. Since this is bounded, so this is also bounded. So its supremum will be a real number. Got it? Not only a real number, it will be, look, it is k greater than equal to n. So first of all, yn will be bounded by the supremum of this and bounded below by, look here, that's you need yn xn less than equal to yn. The way I have defined, because supremum I have taken. Okay, right? Now, if you change n, if you take n plus 1, that means what will be yn plus 1? That will be this, fine. But look, when I take yn plus 1, I'm taking supremum of a smaller set. Okay, a smaller set of a supremum is smaller, right? That means yn plus 1 will be less than equal to yn. Got it? That I have explained. Okay.
Yes, sir.
That means what I am getting, yn is a decreasing sequence. Look here, the monotone sequence is coming into the picture. Yn is a monotone sequence. Got it? Okay. Of course, it is bounded below because the whole thing is, look, yn is a decreasing sequence. No. Look, note that since xn is bounded, yn is also bounded sequence that I told you, because yn, whatever I am doing in, xn is bounded means xn is lying in between this interval. Look, each yn for all n, since xn is bounded, you have this, then each yn will be in this interval. Okay, so that means yn is both bounded below and bounded above. Okay, right? Now look, here I am using the monotone sequence idea. First of all, yn is a decreasing sequence and yn is bounded also because xn is bounded. Look, each yn will belong here. Okay, right? So that now look, yn is decreasing and bounded below. That I have done before. If you have a monotone sequence bounded below, it converges to the infimum.
Infimum.
That exactly I have given. That yn converges to infimum of yn.
yn.
This infimum over all n. समझ गया? Okay, right? The set. Here the set actually is yn. N belongs to n. So this is infimum. Okay, but this I can write now. Look, inf yn, it converges. It's a number, real number. But inf yn, if you strictly follow the notation, inf n here it is infimum over all n, but yn is this. Sup xk greater than equal to. Wait a minute. Going on. K greater than equal to n. यहाँ पे वो डॉट है या नहीं आ रहा है. K greater than equal to n. Okay, that means let me write it. Now look, that means what you have got? That yn goes to inf yn. This n is a member of the sequence. This n you should understand. This inf yn means inf of this set. Okay. Right? It converges to that. That means, well, now what is this meaning? Inf n. Now yn, I am writing the what I got for yn. Yn is sup of xn, sorry, xk k greater than equal to n. Wait a minute. Look, here, first thing is you should understand the definition. Here, you are choosing any n, okay? Then you are taking supremum over k greater than equal to n. And then infimum you are taking over all n, okay? Understand? You understand the definition, I think. Okay, you are to choose any n, and then you choose that. You choose any n, keep it fixed, and then you get this. Okay, you will get a real number that I already explained for a bounded sequence. Look, in my argument, everything how I am using boundedness of the sequence xn, and then you are taking infimum. Then now n is varying. First I chose any n and kept it fixed. Now I am varying n. So this is giving infimum. So this is a real number. So yn is converging to this. So that this is called by definition. This is by definition. Look, this is limit inf xn. This is by definition. This is a notation. This is called limit inf xn. Okay. Here you can, sorry, this is limit sup xn, because first coming sup. Limit sup. This is easy to understand. If it is ultimately we are getting a limit of a sequence of that convergent limit of a subsequence. I am not saying I am yet to prove that it is subsequence. Something I am getting. So here that sup is coming first. So you write limit sup. Okay. It is also actually the term is limit superior. That I said limit superior of xn. Limit superior of xn. The sequence. You will understand shortly that why it is called superior. Limit superior of xn. In brief, we say limit sup xn. Okay. Now look, if I change the roles of soup and if, same way I will get. That means if I do this, soup in xk k greater than equal to n and n. Look here, this sequence, suppose you call it Zn. Here Zn will be increasing. Previously you are getting decreasing. Okay, and this increasing sequence is bounded above, so it will converge to this. Okay, same arguments basically, only the mirror arguments, reflection into it. Here this will be an increasing sequence. Okay, Zn, where if you put Zn, so it will converge to soup of this. Again, you are having the theory of monotone sequence, because a monotone sequence increasing. Okay, previously I am using monotone decreasing sequence. Okay, so this is, okay, this I will call, wait a minute. Look here, limit soup, because soup is here. Here first inf here. So you call it limit inf. Or actual name is limit inferior of xn. Okay, so I have got two sequences. Yn converges to limit soup and another sequence Zn. Okay, now the thing is that, well, why I'm doing it and that. Okay, why I did that suddenly. Suddenly I have brought something limit in limit soup. Okay. Make sure the limit in limit soup you understand pretty well. You will need in measure theory. There will be a, last time I explained the sequence of functions. In fact, Fatu's lemma, what I told you last time, Fatu's lemma, if you have a sequence of functions, okay, right, you can take R to R. Then for each x you have this sequence. Okay, suppose this is a bounded sequence, then you do limit inf this sequence. So Fatu's lemma deals with this. For each x I can define that. Okay, right, so that now I have defined it, but before that, now you see that we can define. Okay, now the question arises that again in my language is why suddenly we have defined limit inf xn and limit sup xn. In the next result will show that these are the smallest and largest cluster point xn. Note that this result answers all the questions, the three questions that I asked in the previous page. Okay, that means, wait a minute. Okay, here why I answered? Because first of all, you can prove from the definition itself. This will have to be. You should prove it. Okay, limit inf. Some people write one n here and that, but that is not required. That is not required because it is understood from the definition. Okay, so first thing, this is the thing. This follows from the definition that you should be able to prove it. Okay, right? That means basically what you will be proving that soup n in xn xk k greater than equal to n equal to inf n soup xk k greater than equal to n. Look, it's easy to prove actually. This is say, first look at this part and this part. This you are taking infimum. This you are taking supremum. This you called yn. This you called zn. Right? So that for each n you are getting zn less than equal to yn. But actually we proved, it came in the discussion, zn also converges, yn also converges, right? So this actually is the convergence limit of this sequence, and this is limit of this sequence. So if you have two sequences, if you know convergent, then you know that this will be also true. Got it? Okay. So this is this. Limit zn is actually this, limit yn is this. So this. So this is this. Okay. Now what is the importance of that? Why suddenly I did this? Okay, here next result what I am going to prove it. Okay, that you should read. Next time I will explain, but I am explaining the thing that make sure that you prove it, and I will again talk about the proof. Why these are important? Okay, in fact, if you are doing analysis, particularly again next semester, you will do the major theory. You will need all the time this thing. Okay, the thing is, look how many things we will be proving out of this. First, we'll prove that each of them is a cluster point. That means each of them is a subsequential limit. We don't go to prove that. We can prove straight that this is a subsequential limit. So that first thing we'll prove that limit in xn and limit sub xn are cluster points. That's the thing. First thing. That means they are subsequential limits of xn. Okay. Second thing which is important, any cluster point will lie in between that. That means limit in xn is less than equal to any cluster point. Of xn, which is less than equal to limit c. Okay, got this? So first of all, limit and limit sub, they are cluster points. And then I'll show any cluster point will have to lie in between this. Okay. So that exactly I did. Theorem 4.6. If xn is a bounded sequence in R, then limit in xn, limit sub xn are the smallest and largest cluster point. Of course, are the cluster points, but I have not written another thing. Anyway, this tells you that. If I write this, that means this will be the smallest cluster point. This will be the largest cluster point. Okay, that's the meaning. In particular, this will be equal to less than equal to this. That exactly. That will actually this will come from this. Okay, right. Now the thing is how to prove this. Wait a minute. Here I should tell you one thing, that to prove of this one, you need to prove only one of them, limit in xn or limit sub xn cluster points, because and then the other proof that you can have two ways. First of all, suppose you prove limit, if you prove for that. Okay, then the proof for this, if you can imitate the proof of this. You can imitate the proof. This will be some sort of mirror image of the proof. So that you can do it. Okay, and that's one way. But another way you can do it, that is, I've explained that. Okay, now look here. I have given the proof. Next time I'll talk about the proof. It is on page 40. But you go to the end. The above proof for limit sub xn can be modified to prove that limit in xn is the smallest cluster point. Okay. I have proved for actually this here. Limit sub is a cluster point, largest cluster point. Limit sub is a cluster point. First to show that S is a cluster point of X. this S. I have shown in the proof that S is a cluster point and it is the largest cluster point. Okay. Next. But now for the limit inf, I say that can be modified to prove that limit inf, so that look at the proof that your job is to read. I will explain that. Here you'll have to prove two things. First, you'll have to show S is a cluster point, and then S is the largest cluster point. Okay. And for limit n for xn, that means you'll have to prove, we'll call it T, that it is a cluster point first of all, and then you show that it is smallest cluster point. What I am saying here, so you read the proof. It's not difficult to understand. And this proof you can imitate here. Okay, of course you'll have to change the inequalities on that. That I said that the above proof of that can be modified. In fact, modified in the sense it can be imitated. Okay, to prove that limit in xn is the smallest cluster point, or else you can use the above result for limit sub xn to prove that limit in is the more result. You can use that above result. What you will have to prove that? What I'm saying, you can imitate the proof of this to prove for the limit inf, or else you can use this result itself to prove this result. In order to do this, this is very important that to know that what is the relation between limit inf and limit sub. That what I'm saying, look, page 41. Read the top. This is very important comments 1 and 2. First of all, if xn is a bounded sequence, xn is a bounded sequence, if and only if minus xn is bounded, fine. Okay.
Yes, sir.
So look, here I can consider limit inf, here also I can consider limit inf, limit sub. So first thing you can prove that x is a cluster point of this sequence xn, if and only if minus x is a cluster point of minus xn.
Minus xn.
And by using this, you can prove that. Look, I have limit sub. I don't know. I said I have already noted the fact earlier. I don't know where I noted. But limit sub minus xn is minus limit. I think between sub and inf, I have given that result. So that result you can use it. That I said noted earlier. Limit inf xn. Okay. That also the problem. Number 6 of page 27 in AB. Make sure you do it that. Look. Basically, between sub and inf, I have given a result. Same result you will be using here, because ultimately it defined in terms of the sub and inf. So you have this. Look, other result will be, you have basically one result. Because if you have in limit inf minus xn, look, this will be minus of, here you have the minus limit sub xn. Minus. Okay, so basically you have one result. Only thing, it's easy to remember that if you have minus here, that minus will go out. Okay, that means one minus inside. Doesn't matter what limit sub you take. If you have a minus here, then look, the trick is that sometimes if you have xn, I can write it as minus xn. That is exactly I did. So that what I was saying, the proof for that second part of the previous result, you can use this result. You can use this result to prove the second part. Okay, that exactly I mentioned. In fact, I have given a proof for this. Okay, now this is the thing. I have given a proof for this in page 41. Okay. So I think already I have run out of time, but make sure that, okay. So I will continue with the proof of that theorem 4.6, but make sure you read it. And more important thing is that make sure you understand Let me tell you that what you should understand. Before even trying to understand the proofs, it will be better if you understand the concepts. Okay, in general term, I am telling you how to read mathematics. Let me tell you that. This is important. It is not to mug up mathematics. I am not teaching you to mug up mathematics. I am teaching you how to read mathematics. It doesn't matter whether you are reading from some notes or the internet or from books. First thing, you need to understand the concepts well. Okay, this is the first thing. Don't go for the results immediately. First see that concept. So in order to understand the concept, if somebody is defining something, definition giving you, make sure that you understand the definition. Okay, this is very important. The first step, you understand the definition. In order to understand the definition, look at some examples. Look, if you understand the definition well, rather in order to understand the definition well, you need to look at some examples. Look at some examples. That will, concept is related to definition and examples. That means to understand a concept well, you need to understand the definition and related examples. Only then you'll go for some results. First you look for small results. Small results means you have short results, short proof. Okay. Like look here, I am saying if a bounded sequence, then minus xn is also bounded. And by using that, you are proving, so that here in this chapter, you'll have to understand first of all cluster point. Okay, of a sequence. So in order to say, you'll have to look at a couple of examples at least to understand cluster point. And then you come for how we're getting the result. I have given subsequential limit. Okay. And proving that every bounded sequence has a cluster point, I have gone to limit and limit soup. So that it is very vital that you understand what is the limit inf and limit soup. Okay. And rest will follow. I am telling you that. So that this is very important. Okay. This thing. Okay. Limit inf, limit soup. So that here in this chapter, first look at definition of cluster point, then look at the definition of a subsequential limits of a sequence and how I'm getting this, then you come. This is very important. Make sure you spend some time. You should read a few times, 2-3 times at least. It's not you should read 2-3 times at a time. At different times you should read it. You will understand it better. It's a limit soup, limit in. Okay, right? So next thing I will explain that. I put remark on that. That will come in that. Okay. So I will take your class. Is Monday holiday? Hello.
Yes, sir.
Yes, sir.
The next class will be
Yes,
Tuesday,
Yes, sir.
right? So I will
Yes,
take
sir.
the
Yes,
class,
sir.
next class on Tuesday. I will continue with this now. Okay. Fine.
Okay.
Okay.
Thanks.
Bye.
Okay, sir.
Thank you, sir.
Here.
Thank you, sir.
Thank you, sir.
Thank you, sir.
ಜಬರ್ದಸ್ತ್ ಕಿಕ್ಕಿ ನೋಡಿ